My name is Gerrit Grunwald. Some of you might have seen me today in our Duke Turns 30 event. Unfortunately, I wasn't able to attend. I also run a Java user group in Münster in Germany, where I live, for I think now 17 years. And this is the best thing ever. So who's the first time here today? That is a very good choice. Keep going, because without my Java user group, I wouldn't stay here. I wouldn't have my job and all the other stuff. So Java user groups, this is the best thing with the whole Java ecosystem. Okay, but that's enough about me. Memory management, right? In the JVM, it's automatic, right? So why care? So who of you set a specific garbage collector for your production code? One?
Not anymore.
One. The rest just takes it as it is, right? Default. And it works, right? Good. It's not bad. It's okay. It's a good choice. Anyway, sometimes you run into problems, even you will sometimes, or you had the experience in the past. Some things like, oh, we have a problem. We have no idea what it is. Just put more CPUs. Didn't help. More memory. Also not. Then it's probably garbage collection. And then it makes sense to understand a little bit about it. So this is not a deep dive. This is one overview, gives you some ideas, but should help. So it has an impact on application performance, absolutely, and also on the responsiveness of the application, right? And also on the system requirements. So that means CPU and memory. All this is impacted by garbage collection. And to give you a little recap how it works, so we have threads in the JVM, and every thread has a so-called stack, and on the stack we put so-called stack frames. And this is for every method that will be called, get a new stack frame, okay? And in that stack frame we save primitives and references, and that's it. And this is dynamically, it shrinks and grows dynamically, so we don't have to take care about it. But you probably saw something like Stack Overflow. That's if you run out of memory in the stack, right? It's not related to the heap. And this is thread safe because it's only local access. So, and we don't do garbage collection there. But this is very important because garbage collection starts there in these stack frames. Sometimes if you read about garbage collection, you often read about roots. We start in the garbage collection roots. This is the roots, the stack frames, okay? And we call a method, a new stack frame will be put on the stack. Once the method returns, it will be removed from the stack. This is how it works, okay? Then we have the heap. And in the heap, we store the actual objects. So this is where we really take the memory, right? The references and primitives are not really that big. But here we store the objects. This is shared access. So it's not thread safe, and we need to do garbage collection here in this area. And then we have a third area, which is so-called metaspace. And there we have class metadata, constant pool, and other stuff. But we don't talk about this part. And in principle, you can just remember it as everything that the JVM needs to run with classes is in this space, right? But we don't talk about that one. And as already mentioned, Stack Overflow is in the stack frames here, and the out-of-memory exception is in the heap. And these are the two memory exceptions that you can get when you work with the JVM. So by the way, who's someone working on OpenJ9 except you? Because this is a little bit different. It's a JVM from IBM. They also have a JVM. And to just give you a little background, so we have a spec for Java, for the language, and we have a spec for the JVM. And when Sun created the JVM, they followed the spec that they created and created the JVM hotspot, okay? And IBM did the same. They just took the spec and said, we create our own JVM, and this is J9. It became OpenJ9 in the meantime. You have to correct me if I'm wrong. So it's both JVMs. They both are compatible. So you can run the code on either of them, but they come with different features, and this is also with the garbage collectors. They have different garbage collectors, but they work with the same principles. I can give you one example that I looked up. Okay, I hope you can read it even in the back. It's a little bit small. Pretty simple example. I have a record person, and the toString method returns the name. That's all. right? So I create 4 instances, and then I put them in a list, and then I print out the first one. Simple. The stack frame, we have the stack for the thread 1. The frame for the main method contains the 4 references for these 4 person instances, and also for the list. Okay? And now the interesting part, there's the heap. And in the heap we have the actual objects, and these references on the stack frame point to the objects on the heap. Okay? This is how it works. And this is also the reason why we name this stack frames roots, because when we start with the garbage collection, we start here at the references, and we follow the references into the heap, so we can identify the objects. That's the idea, but we come to that in a minute. And you see, the list object has internal references on the heap that pointing also to the objects, okay? So and then all of these are reachable. That means I can reach these objects in the heap when I start from the stack frames, from the roots, okay? So now if I set P1 to null, then the reference is gone. And this is something that mainly juniors sometimes get wrong, because they think, oh, I set the object to null, it's gone. It will be garbage collected. But remember, it's also in the list. The list has an internal reference to the same object. And with this, I can still get the value of this object by calling just the list and get me the first object in there. So you can still reach it, right? So it's not dead. It won't be collected by the garbage collector. Okay. When I now set the list to null, then all the references are gone from this to this person 1 object, and only the 3 ones in the middle I can reach from the stack frame. The rest still takes the memory in the heap, right? So the heap is still allocated, but I can't reach it anymore, and that means it's literally garbage. And someone has to clean it up. How to do it? Garbage collection. That's the main idea, okay? There are different ways of doing that. Garbage collection is just one form of automatic memory management. There are other ones like automatic reference counting, for example. Is someone doing Swift here? Except me? Swift is also using automatic reference counting. It's a different approach. There's no worse or better. It's just a different thing. Both have their advantages and disadvantages. Okay, it's a form of automatic memory management. It's made to identify and reclaim no longer used memory, ensures efficient memory utilization, and this is the most important part. It takes away the burden from you to do malloc and free. Someone with a C background here? Yes, you love it, right? Malloc and free is really great. And that's exactly the point why someone smart came to the idea, oh, if we can do that automatically, we don't have to take care about it, because there's a huge problem in C that especially when you start with C, you mess it up usually, and then you always have some memory leaks. And this was one of the intentions. Okay, so we have 2 different kind of collectors, and we talk about conservative collectors and precise collectors. This is, you don't have to remember that, okay? Not important. I can provide the slides afterwards if you share them. I don't know if you share. Okay, so I will provide the slides. I will just explain it. You don't have to remember all this stuff because that's way too complicated. But the difference is the conservative collectors, they don't really fully identify all the live objects on the heap. They use so-called bit patterns. They apply them and say, oh, that looks like this is a live object. Yeah, I assume it's live. This is how it works. So they might be wrong. So they're not really able to do that. Where precise collectors can absolutely identify all the live objects on the heap. Right? So, and this is also the reason why in the JVM we only have precise collectors. We don't have conservative ones. This is just if you stumble upon that. If you read something about garbage collectors, sometimes you read about conservative. We don't have that. Not interesting for you on the JVM. Okay, and the precise collectors have 3 different phases where when they work. So the first thing is the tracing. And the tracing is we have to find all the live objects on the heap, right? So that means we don't find the dead objects, we only find the live objects. This is tracing, and we do that by following all the references. And then we have freeing. Freeing sounds easy, but yeah, we just remove the stuff. Easy, right? No, it's not. Freeing is not for free. And I can show you in a couple of minutes why, because it's more complicated. And then there's compaction. Someone old enough to remember, yes, you probably, to remember Windows 3.11, there was this defragmentation. Yes, and we will see that, because this is, then I can explain compaction. Who knows stop the world, what it means? Okay? It's not a problem if you don't know. I will explain it to you. But you have to know what that means, because this is one of the reasons why we have, I think, at least 5 or 6 different garbage collectors in the JVM. And the reason is we have application threads, right? They work and allocate memory, and we use that memory, and at some point we have to do a garbage collection. You saw that old stuff is sticking around and we have to remove it, right? So to do that, we stop the world. So that means we have the application threads running, and when it's time for garbage collection, we trigger it by sending a save point signal. That's how it's called. And that leads to the fact that all the threads will stop in a safe position. Safe means they are in a safe state, right? So every state is really secured here. And then no application thread is really working on the memory anymore. That means the JVM can now start and clean it up, do the garbage collection. This is the orange area here. Once we are done, we continue the application threads. This orange area can take up to seconds. Depending on the heap size, worst case, 30 seconds. And in this 30 seconds, nothing happens. Your applications just stop. Nothing. It looks like it hangs. In the background, we do the garbage collection. This is the reason why this is so important. We would like to have the garbage collection, the stop the world pause, as short as possible. Because then you have the impression it's like continuous running, right? Especially if you have something like, let's say you have a trading application. Right? High-speed trading is the worst case, because there you have milliseconds, and you have to make sure that all the transactions are really continuously going, because if you stop for 5 seconds, means you lose a lot of money. Right? So this is one of the reasons why this is important. These days, not so much, because the default garbage collector, at the moment it's G1, and we will come to that one. It's quite good, because it's fast. But in the past, where we didn't have G1, this garbage collection process that really caused a lot of trouble, right? So remember, if you see STW or stop the world, then you know what it means, right? We halt the application, then we do the cleanup, and then we continue. So now let's take a look at the collectors, and I don't mean the collectors in the JVM, but the basic principles. So we have different kind of. We have non-moving collectors, and I will explain what it means, non-moving. Mark and sweep. Probably all of you heard that, right? Who knows how it works? Okay, good. It's not important. If you don't know, no problem. This is my heap, and everything I show you is very, very basic, right? So this is not the reality, but it gives you an idea. The gray cells here, these are the memory cells, if they are empty, unused. As soon as I allocate them, they are blue, right? If they are dead, that means I remove the reference, then they are purple. Then they are just dead. Can't reach it anymore. Garbage. If they have this little red square in the upper left corner, then the garbage collector found it and said, okay, this is a live cell. I identified it. And if there's a number inside, then it means I told you we stop the world, we find the live objects, we remove the dead ones, and then we continue. That means the live objects survived a cycle. This is the number. So if you have an object that is, let's say, for the whole application lifecycle, then you see a huge number there because it survived all the garbage collection cycles. For this collector, it doesn't make sense at all. But there are other collectors, and we will come to that, where it really is important to know how often did this object survive the garbage collection cycle. So let's take a look at it. So we start allocating here, and you see objects die young. Right? They won't get really old, most of them. Once we reach the end, means memory is full, we stop the world, we mark the live ones, and remove the dead ones. Right? So stop the world, mark, remove, continue. We didn't move anything, right? No compaction. We just removed the dead ones. You see already the problem. The first run is nice. The second run, third one, it gets cluttered, right? Windows 3.11, disk defragmentation. This is exactly this. It's the same thing. So now I told you freeing is not for free. The reason is, once we mark everything that is live, we can't just go and find the rest, the dead ones. We can't find them easily, right? Because we have no references. So what do we need to do? We have to check every memory cell on the heap. Check the cell. Is it live? Is it dead? Is it free? Okay, next one. And so we find the dead ones, and then we can remove it. This is how it works. The larger the heap, the longer it takes to free the heap, if you follow this principle, right? That's the reason why freeing is not for free. I don't really go into the details here because it's way too complex. But you get the idea. And in this example, it's also not a big problem because every object that I allocate is exactly one memory cell. In reality, you have big objects. Let's say you need 15 cells in one piece, right? It gets harder and harder to find this. And then that means you run out of memory. That's what happens. This is an out of memory exception with this collector, okay? But this is the very basic collector. We stop the world, we mark the live ones, remove the rest, continue running, okay? This is.
If I understand correctly, this is a naive implementation.
No, this is an implementation that was used in garbage collectors. This is one of the basic principles, which is, it's not a bad thing. It's just because it's cluttered doesn't mean it doesn't work, right? So it works, and it's a good collector, but it has its problems, like fragmentation is one of the problems with this collector. The advantage is we don't move things around. That means we don't copy cells, because the problem with copying cells is then we have to update the references that coming from the stack frames and pointing to the object. So if we move the object to another place, we have to update the reference. This is an additional step, takes time, right? And this is the reason why the non-moving collector has its advantages, but also disadvantages. Fragmentation, that's the biggest problem with this one. Okay, leads me to moving collectors, and we have two different ones here. There are more, but I just talk about these two because this is the stuff that is used in the JVM. So we have the compacting collector and we have the copy collector. The first one we will look at is the compacting collector. And that's pretty much the same as the other one. This is mark and compact. And this is in use in actual garbage collectors. You will now see the exactly same thing that we saw before. I start allocating memory. Objects will die. We stop a little bit earlier. I think I stop here because I need to leave some headroom, right? Some empty space at the end of the heap. Because what we now do is we stop the world, we mark the live objects, and then we remove the dead ones, and then we compact everything. In this case, I will copy everything to the upper left corner, right? And to be able to do that, we need some space some temporary space where we can copy objects, move them around, stuff like that. This is the reason why we have to keep some free memory at the end. Let's take a look at this one. It's like I said, it's exactly the same stuff. We allocate memory, objects die quickly. The reason why they die quickly is, I will explain it to you. Stop the word mark, free, unmark, compact, continue. Okay? You see this additional step of copy everything or move everything, the compacting step that also includes updating all the references that coming from the stack frames. But the big advantage is every time we continue running, we can freely allocate memory because nothing is in front of us, right? It's empty space. That means allocation is fast because the mutator, that's the part that allocates the memory, doesn't have to find the free spaces. It can just allocate. And this is good because this is application performance. The faster you can allocate, the faster the application will run. Okay, this is what we aim for. Fast allocation. This is very good for an application. Because otherwise, we talk about memory pressure. That means if you allocate as crazy, right, then the garbage collector has to keep up with that. And that means as long as we can just allocate freely, it's good because the application can work fast. Okay. Problem with this one, headroom. Depending on the heap size, it can be up to 50% that you have to leave free for the copy stuff. Okay. But apart from that, this collector is in use in the JVM, so it's not a bad collector. Okay, copy collector, this is completely different, and you will see why. This looks like this. we have two spaces, right? They have the same size. One is called to space, the other one is called from space. And they will toggle. Every time we do a garbage collection, the to space becomes the from space and vice versa. And the way it works is, and it's quite smart, we allocate in the orange area first. And when it's full, we mark all the live stuff. And then we copy the live objects, and in between we toggle, we copy the live objects into the then to space, right? And the good thing is, because the gray area here is, there's nothing in there. That means we can just copy them and it's automatically compacted, right? And the other advantage is, once we copy all the live objects, we know that the rest in that now orange area is garbage. We don't have to check every memory cell because we copied everything that was live. We copied in the other one. We can just clean it up. Freeing is fast in this one, and it's always compacted. So let's take a look at that one. So we start allocating at the moment it's the to space. You will see when I stop the word, I toggle the two spaces, and then it makes sense. We copy from the from space to the to space. So now stop the word, mark, copy, remove. Always compacted and continue. Now we do the same thing on the right side. If it's full, we stop, mark, copy, and so on. So this is the whole procedure here. You also see the disadvantage, obviously. There are two disadvantages. One is obvious. We need twice the amount of memory. What might be the other one? Any idea?
You're copying objects that might have stayed in the same place.
We copy objects every time. If they are long-living, we have to copy them all the time. Right? That means updating references. Even if we know that this object will never die, we have to copy it, right? Which is a disadvantage, obviously. Okay, but this is the principle. You get the idea. Okay, that's a copy collector. So in principle, this is all you need to know to create garbage collectors, because these are more or less the three basic principles that you can also combine. And that leads me to generational garbage collection. Who heard about that one? Because I told you, objects die young. Right? They don't get really old, most of them. And one of the reasons is, and this is a good basic principle, you have to create lots of small methods because it's easy to maintain. Every method creates garbage. When it's called, you create a stack frame. When you return, you remove it, so you have dead references and dead objects, so you have garbage. That means lots of small methods create lots of garbage. Okay? This is one of the reasons why objects die young. So, weak generational hypothesis is exactly what I explained. Objects die young, and you know the reason. And there's a chart that you probably saw before. So we have the number of objects on the y-axis, and then we have the lifetime of the objects. So that means how old they get on the x-axis. So, and usually it's like this. So we have lots of objects that die very quickly. Then we have a couple of objects that live a little bit longer. And then we have just a few objects that live for a long time. Okay? And this is not only for Java. This is in general. For all the languages that are around, this is how it works. And now if we use the principles that we saw before, we can create a garbage collector for this specific behavior. So that what we do is we use the area where the objects die young, and in this case we name it Eden. You might have heard that when it comes to garbage collection. This is the place where we allocate memory, and it can be small because most of the objects will directly die. And this means we have to do a lot of garbage collection in this yellow area, but because it's small, it's fast. It doesn't take long, okay? And then we have the medium living objects where they might live a little bit longer, and for this one we use a copy collector, right? And the reason why we use a copy collector is that there is still something missing, and I don't know exactly how to pronounce it. Is it tenured space or tenured space or?
Tenured.
Tenured, yeah. Tenured. So I name it like this. Might be wrong, but that's the blue area. This is for objects that live for a long time. And you might wonder, okay, if we just have a few objects that live for a long time, why is the blue area so big? Any idea? It's pretty simple. Everything that survived a couple of times from the medium living objects, right, so which is old enough will be promoted into the blue area. And the blue area will fill up slowly because it's just a few objects. That means it takes a long time until we have to do a garbage collection here, and that is good. Problem is, once we have to do a garbage collection here, it takes long because this is a huge area. That's the drawback, right? But if your application, maybe a microservice, runs short enough so that this one will never fill up, we don't have to do garbage collection here, okay? So it all depends on how you size the heap for your application and on the application behavior and all these kind of things. Okay, so now we have these different areas, and we talk about the young generation, if we talk about the short and medium living objects, right? And we talk about the old generation if we talk about the long living objects, okay? And then we can do different collections here. We talk about the minor collection if it's only the young generation, because this we have to do quite often, right, in the young generation. And then it's a major collection if we do it in the old generation. And then you can do both, which is the so-called full collection. It's minor and major after each other. So this is the worst case that can happen. Okay, of course I have a demo for that. So we will see, I allocate memory only in the yellow area. Only a few objects will survive. I copy them into the copy collector, right? And in this case it's called survivor spaces because objects survive and so on, right? So, and then in my demo, when they survive 3 garbage collection cycles, the objects will be promoted, that's how you call it, into the old generation, into the blue one. We do that cycle once, and then you will see, then I'll do a fast forward, and then you will see that this blue area will fill up slowly, and it's like a wavefront. It's moving through this blue area. And even there, objects will die. Just takes longer. So that means you will fill up the blue area with objects, and over time they die from left to right. And then in the end, we just have on the right side some live objects, right? So once this is full, in my example, I do a full collection. First of all, I clean up this one, the blue area, and this is mark and compact. And this is exactly how it is used in the JVM. The old generation is mainly done by mark and compact. And once I did that, then I copy all the live objects from the young generation also in the old one. And so let's take a look at that, because this is interesting to see. And I hope this gives you a better understanding with the copy collector, the survivor spaces, because when you see how it works, especially when it's now fast forward, then you see how it's toggling all the time and stuff will be promoted into the old generation. So first we do this thing, do that for some time, and now when we have objects that survive 3 times, in the 4th cycle they will be promoted. I guess maybe even in the 3rd one. Now. And now it's fast forward. Now you see how it works. We do lots of collections in the Eden space. Doesn't matter, it's small, right? And lots of collections in the copy collector, also great, no problem. But once we reach the blue one, and this I will slow down again now. Now there's not enough space left in the blue area in the old generation. Now we have to do a garbage collection here. That means we stop the world, we mark, clean, compact, and then we copy everything from the young generation into the old one, and then we continue. This is a full collection. This is the worst case you can have. And then we start again from the beginning, right? Because then everything's clean and we can start. So this is how generational collection works. And the big advantage of a generational collector is you can collect the young generation quite often. That means it can be really fast, right? If you don't do generational, then you always have to, then you just have one space, right? And then you always have to do the collection in the full space, and that's slower, okay? Okay, so this is generational garbage collection, and there's one collector in the JVM that works very similar to this one. It's called CMS. It's already deprecated. And in the IBM OpenJ9, there's a very similar collector, and it just starts with the copy collector. So there's not the yellow space, it's just not there. So instead of having an Eden space, they directly allocate always in the copy collector. But you see the principle is the same. These are the basic principles, and you can combine them to different garbage collectors. In this case, this is a generational example. All right, now I have to explain a few things that can happen, and sometimes you will read about it. It's the so-called remembered set, or also card table. So sometimes you will read card table, sometimes people name it remembered set. And it's if you have different generations that I showed you, right? The question is, if I do a minor collection, that means only in the young generation, and I have a reference that's not coming from the stack frames, but it comes from the old generation and points into the young one, I won't find it. And let me show you why. So you see here I have the young generation on the left side, right? And I have the old generation on the right side. Now I have the stack frames on top. This is the roots where we start. And I do a minor GC in the young generation only, right? So the collector only takes a look at the young generation. So now I have references coming from the stack frames, easy to find because we can just follow. I have internal references, also easy to find. And then I have this one. There's a reference coming from the old generation pointing in the young one. But I only do the garbage collection in the young one, so I don't see this reference, right? Because the collector doesn't follow the other ones. We just do it in the young one. How can you find it? Well, this is the so-called card table. So the JVM looks that up, so it knows exactly, oh, there's a reference, and it tells the garbage collector. So the garbage collector can, even if it does a minor collection, it can look up the card table and find these references. And it knows, okay, there's another reference coming, and marks it as live. Because otherwise it would remove it, and then it will crash. It's all these things you have to keep in mind. So the only thing you have to remember is if you hear about remembered set or card table, it's intergenerational references. That should be enough, right? So it's this is handled by the card table. All right. That's the easy part. That's stop the words, serial, no problem. What about concurrent collection? So it means I would like to allocate memory, and at the same time I would like to clean it up. So no pauses more.
Without stopping Without stopping the
Without stopping the world, that's the idea. Well, concurrency is hard, right, as we all know. And I didn't really went into marking, but this is the step when the garbage collector starts following from the roots into the heap, right? It finds an object and says, oh, I found it. I can reach it. That's the first thing. And then afterwards it flips a bit and says, now it's marked. This is live. There's a specific bit in the header of the objects. So if we would like to do that concurrently, and this is an example I took from Roman Kenke. He did that on the JVM Language Summit where he explained Shenandoah. And these charts are just good. That's the reason why I took it. We start from the stack frames again, from the roots, and the garbage collector now follows the references in the heap, right? It follows the first one, say, yep, I can reach it. Yep, I mark it, it's live. And then it went on to the next one. But now suddenly the application thread decides, oh, you know what, this reference, I just remove it because I don't need it anymore, and I establish a new one here. The garbage collector already passed the first memory cell. It can't see this new reference, and it also doesn't know that the other one was removed. So that means it continues following the references and marks everything that it can find, leaving out the one at the bottom, even if it's reachable, theoretically, right? So what happens, it will just remove it, and that's not a good thing. So the problem is, how can we now make sure that it will find this reference to the new memory cell? Well, there's something called barriers. Did someone hear about that? It's a very basic principle. The main idea is you can think about, we have read and write barriers. It means every time you try to access a memory cell, either for reading or for writing, doesn't matter, you have to execute some code first before you can access the memory cell. That's what it means. Sounds strange, right? Because if you think about it, how often we read and write to memory, every time you have to execute code, the code must be very small, very fast, right? In fact, it's for all garbage collectors just one CPU cycle, which is more or less nothing, so that's okay. So it's a mechanism that is used, like I said, this is, for example, used for the card table, for the intergenerational things. There they use read and write barriers. We don't go into detail, and you don't have to remember that. It's way too complicated. The other thing where it is used, and we will see that, is when the mutator, so the allocator and the garbage collector, they can kind of communicate using these barriers, right? So they can talk to each other by using the barriers. And this is another thing where they are used. just already mentioned, we have more or less 75% reads in a typical application and 25% write access. If you create a read barrier, that means this code has to be very efficient because it will be triggered so often, right? This is just something you have to keep in mind. But as I mentioned, this is way too complicated to go into detail. Just you have to remember there is this concept of barriers, right? Where you have to execute some code either for reading or writing. So if we use that for the same example, so we start again with the collector, and now on every memory cell we have this code, right? That has to be executed if I would like to write something. In this case, it's a write barrier. In my example, the write barrier, the code says, if you remove a reference, right, then mark the cell that it was pointing to as reachable, not as live. We have, it's called 3-colored marking. So we just mark it as reachable, that's it. So that means garbage collector, find the first one. Yes, I can reach it, I mark it as live, goes to the next one. The application thread steps in and removes the reference and now hits the write barrier. The write barrier says, oh, you removed something. This cell, and it also installs a new reference, and this cell will then be marked as reachable. That's it. This is done by the write barrier code. Garbage collector still has no idea. It just continues marking stuff. Yeah, I found everything, I'm done. And now the additional step is a so-called remarking phase. So once the garbage collector is done with marking everything, it starts from scratch and only looks for reachable cells that have been marked reachable in between. Right? This is another stop the world pause, but which is very small. Right? This is the reason why it's not really mentioned as stop the world. And then it finds this one, and because it can reach it by the new reference, it will mark it as live. If there wasn't a new reference here, then it would remove it, because then it can't reach it, even if it was marked as reachable. Right? So this is the whole thing. So that means we need 3 colors, reachable, live, or not visited, to make sure that we can do the remarking phase. But it's an additional step. We have to do an additional run just to find all the stuff that was marked in between. Okay, that should be enough, right? It's complex enough. But we have a different thing, which is also interesting, which is concurrent copying. Remember, if we do the compaction, where we move stuff on the heap, well, if we do that in a stop the world manner, then it would look like this. So we have the objects on the left side, and we would like to move it to a new space. So we stop the world first, then we copy the object to the new location, and no thread is now working from the application side, so it's no problem to copy that. Then we install a forwarding header here, and then we update all the references. Once we are done, we remove the old object, and then we can continue. This is also some of the problems with some of the garbage collectors, because we have to keep the old object for as long as we have to update all the references. Right? So that means for this time we have both objects on the heap. Right? So that means we only can remove it once all the references have been updated. This is important if it comes to physical memory and memory mapping. Okay, so once we're done, we are good to go. Nice. Okay, but we said we are doing concurrent, so okay, let's do it again. Concurrently, we don't stop the world. We just copy the object, no problem, right? Okay, then we update, forwarding header, and go. And now it happens that both objects are reachable, because we have stack frames pointing to the old and the new one. And then suddenly, application thread stepped in and said, oh, and one can reach the one object and the other one the other object. It's not really good, right? So we have to find a way to avoid this situation where both objects are reachable on the heap. And there is something that is called Brooks pointer, which is also used in Shenandoah, which is one of the collectors. And in this one, what they do is they install an additional forwarding pointer on each object header, and this points to the header itself. It doesn't make sense at all, right? If you see it like this, like, what's the point? Well, it becomes interesting once you copy this object to a new location without stopping the world, and then this header points to the forwarding pointer points to the new object. So at this moment, it's not reachable by any other thread. It's just sitting there on the memory. And now this is the important one. There's an atomic operation where we just change the forwarding header from the left object, from the old one to the new one. This is atomic, nothing can step in. And then we update the references. And then it doesn't matter where the threads walk through, because if it addressed the old one, it will be forwarded to the new header, and if it's already accessing via the updated references, it will also find the second one. Okay, you might have a point where you say, wait a moment, because what happens here? I copy the object. If now a thread accesses the left side, right, then objects are different. Yes, this won't happen, of course. There is a way to prevent that, right? So the important part here is that this operation is atomic, so nothing can step in here. It's just putting the pointer from the own header to the other one, and then from that moment on you can access only the new object. But once again, we have to wait until all the references have been updated, and then we can remove the old object from the heap, okay? So this is concurrent copying. It's a very basic principle for a very complex thing. So I hope you get the idea how it works. And that should be it with all this complex stuff. Now we look into the things that are real, right? So the other stuff sounds sometimes unreal. We start with the serial collector. This is the oldest one in the JDK. It started with JDK 1. And there's a reason for the name. It's available in all JDKs, even today. And it doesn't mean just because it's old, it's a bad collector. It could be even the best collector for your use case. You just might not know it. So who's working with microservices here? Who's working with small microservices? Let's say 2 GB of heap and smaller. Okay, smaller than 1.8 GB. Yeah. And if you don't set the garbage collector, you will get this one. Because this is, the JVM will pick this one for you. There are specific rules specifically for the serial collector, which are based in the past, these rules, right? And this is the rules. If you only have one CPU, or you have less than 1.8 GB of RAM, then it is not a server. That's the definition. And this comes from way back, 1996 or something. Because at that time, nobody could imagine that a machine with less than 1.8 GB, that couldn't be a server. This is just not enough memory. And if it just has one CPU, nah, no server. These days, where we have microservices, in Kubernetes, where you can have 0.5 CPUs and stuff like that, suddenly this is relevant again, right? Because these rules lead to the fact that if you come from a 2 GB heap, and we know cloud is expensive, and your boss comes to you and says, can we do something? Do we really need 2 GB? You say, we can probably go to 1.5 and it will work. You switch to 1.5 and suddenly you see some strange behavior, because sometimes the service stops working because you have this collector. If you specify your own, it's fine. If you don't be aware that it will be selected for you, okay? The problem with this collector is, and this is the name serial collector, you see it on the left side, it's young generation and old generation. We stop the world, and then we have one thread that does the garbage collection. And you know, in Eden, garbage collection is often, because it's small, Eden space, okay? That means we have to do a lot of garbage collection, and we only have one thread that does it. That makes it slow. Full or major collection, same, only one thread does the garbage collection, serial collector, okay? And it uses mark and compact as algorithm. Okay, but anyway, this is not a bad collector, right? Because if you have the right amount of heap for your application or service, this could be the best solution for you, right? Because the good thing with this one, CPU overhead is pretty low. That means if you restrict it in your CPUs or in your memory, this is a good collector, right? You might have to check out the pause times, because it can have long pause times. This all depends on your application. So there's no rule of thumb where you can say, I have this microservice. Is this the right collector? I don't know. Right? It really depends. But it's more or less not a bad collector for microservices if they are small and short-living. Okay. Leads me to the next one, which is parallel. And you might already guess what this means. Again, It's available in all JDKs, and it's also called the throughput collector, and there's a reason for it. If it comes to throughput means time you spend in your application versus times you spend in the garbage collector, then this is the fastest collector you can get. It's faster than ZGC, right? Depending on the machine that you use. But still, very low CPU overhead, still, right? Latency is low, throughput is high, so it's a quite good collector. And you read something like heap size medium to large. And you might ask yourself, yeah, what does it mean? Well, depends. If you have asked me 10 years ago, I would tell you, oh, medium size, maybe 1 gigabyte. Today it's maybe 4, right? This changes over time. You have a feeling what it means medium or big. So, for example, who's working with a heap bigger than 64 gigs here? See. That means this is a big heap, right? Depends, because we have customers, they have a heap size of 21 terabyte. No joke. This is a big heap, right? So then 64 gigabytes sounds like, this nuts, it's nothing. But depending on what you do, this is really relative. You can't really say. But this is, if I talk about this, I mean smaller than 4 gigabyte in this case, okay? So how this works, different. You see what happens in the Eden, or in the young generation. We have stop the world, and then we have multiple threads that do garbage collection. Can be lots of threads. Makes this collector really fast if you stay in young generation. Old generation, 1 thread. That's the drawback. Once you have to do a full or major collection, it can lead to really long garbage collection pauses. Right? Again, it depends on how you size the heap for your application. If you never have to do the major collection, great. Then this is more or less the fastest collector you can get. Okay? And that was the default collector from JDK 5 to 8. So in this case, if you have 5 or 8, is someone on JDK 8 still? Or below, maybe 6 or 7? Yeah, okay. 6? Yeah, then this is the default collector for you. And it's not a bad collector. But some people think, in JDK 8 there was G1. No, it's not true. It came with JDK 9. You could enable it in JDK 8, but the default was still parallel. All right, so this leads me to CMS. And CMS, it's deprecated. It's even, who's on JDK 11 here in the room? 17? Okay. And the rest 21?
22.
Okay. This was removed in 14, so all of you don't use it except you. You can still use it.
We have different applications with different.
Okay, good. Well, on the 6 you can still use it. So this is concurrent mark and sweep. And this one looked very much the same as the one that I showed you with the generational garbage collector. This is how it looked like, more or less. Like I said, very basic, but the idea was exactly like this. And it was available from JDK 1.4 till 13. It was already marked as deprecated in JDK 9, and then they removed it in 14. So if you have 14, you can't even enable it anymore. You could get an exception at the startup. It's not there. This was the first collector where they decided, we need to predict the pause times. We have to make sure that there is some hard limit, like 1 second. So garbage collection pauses have been shorter than 1 second. The max was 1 second for this collector, which made it predictable, which is good, because then you finally can say, okay, the application will work and the max pause times will be 1 second. This is cool. The reason why they removed it, or one of the reasons, was it wasn't compacting. So that means we have fragmentation on the heap in the old generation. And that was problematic. Right? So that led to problems. And the other thing was that the code was so complicated that the developer said, we don't want to maintain that. I'm not really keen on doing that. So this is the reason why it was deprecated. And you see the diagrams get more complex because this was partly concurrent. So it could mark stuff concurrently. And I think even sweeping was concurrently possible, right? So partly concurrent, so not fully. Like I already mentioned, removed from JDK 14 and deprecated in JDK 9. Okay, and then we get to the nice one, G1, because this is totally different from the other ones. The other ones really are shaped like these big blocks, like Eden, survivor spaces, tenured space. So this one was the first one that looks like this. It's a region-based collector. It's different, right? And the region size, one of these squares here, this is one region. And you see on the left side, it depends on the heap size that you define, XMX, right? So it can be, the max region size could be 32 megabytes, which is not really big, right? And that means if you have to do a collection in one of these regions, it's fast because the regions are small. And the idea is, this is when it's empty. If it's in use, looks something like this. The idea is, the name is garbage first, right? And there's a reason for that. So we have, and you see we have Eden regions, survivor regions, tenured regions, humongous regions. Humongous is such a great word, I love it. Humongous regions they will be used if an object is bigger than half of the region size. Let's say you have a 32 megabyte region and the object size is 17 megabytes, then you get the whole region for that object. Sounds cool, right? Has a problem. The rest of the region is empty and you can't use it anymore. And in fact, that leads to problems. So we have customers where they know exactly the memory pressure of the application, so that means the allocation rate and all that. Still, if they size the heap according to their needs, they run into out-of-memory exceptions. The reason is most of their objects are bigger than half the region size. So they run out of memory because they get everywhere humongous regions, and they won't be moved. It's the same as the old generation directly. And then they have a lot of empty space that they can't use, right? So, but this is stuff you have to analyze. This can be a problem. It doesn't have to be, but for some application, and then it's most of the times it's enough to change the heap size a little bit to adjust it, right? Okay, so back to garbage first. We see the yellow regions. That's the Eden regions where we allocate memory. Now we have a specific number, and that's all configurable. We have a specific number of Eden regions. In my example, I have 6. When I run out of these 6 regions, I have to do garbage collection there. And what I do is now, I take the 2 regions that have the most garbage in it, garbage first. And then I take all the live objects from these regions and put them into a survivor region and clean them up. This is like kind of copy collector, right? We copy them from the Eden spaces into the survivor space, okay? Only the live objects. And why do we use the ones with the most garbage? Because we have to copy just a few live objects. This makes it fast. And the most of the stuff is garbage, we can just remove it afterwards, right? And because we copy the live stuff out of it, it's called evacuating. We evacuate the live objects into a new region. That means all the rest is garbage. We can just remove it directly. We don't have to check for the freeing, okay? So let's take a look at it. Does it start? Yes. So we will allocate 6 Eden regions, and then we do the first garbage first collection and copy the live objects into a survivor region, and then we continue with this game for some time. You see objects will die. First one. We needed 1.5 survivor region here. And we continue allocating, and once the survivor regions are full, I think I have 3, then they will become old generation, the blue ones. And so on. And you see already the benefit here. It's very flexible. We have lots of different regions, all small, and we can reuse them for all kinds of types. So it's not fixed. So a region can be an Eden region, and afterwards it can be a survivor region. It's no problem to do that. And because of that, and because of the region size, the whole collection cycle is very fast. Right? So this is the idea behind region-based collectors, and all the new collectors are region-based. So this is not the old stuff where we have the huge regions or huge areas. This is not anymore. So this goes on forever, so I just stop it here. This collector, which is now the default one, yes?
During the collection, it only does one region? It doesn't do multiple at the same time?
Yeah, it does multiple. So in this, this is just easier to show if I do it like this. You just should get the idea. This is what I said. This is very basic visualization to give you an idea how it works. In reality, it's way more complex because this is also all thread-based. So different threads have different regions and all that. So it's quite complex. So the idea here is that because it's so fast, we can more or less guarantee that 200 milliseconds is the fastest or the longest pause. That makes it so appealing as a default collector because, as you saw, for most of you it works, right? Because this is usually good enough. Except you come to very, let's say, high-performance applications or high-speed trading stuff where you need even shorter pauses. But for the majority of applications, this is quite good collector. And that means it works for mixed workloads, for large-size enterprise system, and so on. You also see the overhead is a little bit higher already, and it's partially concurrent, like the CMSs. It can do concurrent marking, concurrent freeing, stuff like that. It is parallel, so we have multiple threads that do that stuff at the same time. And heap size is, again, medium to large. The sweet spot is 16 gigs. So this collector is at its best performance with 16 gigabytes of RAM, heap size. 32 is also okay, but if it gets bigger, performance drops a bit. If it gets smaller, also drops a bit. So the best performance is really with 16 gigs. Okay?
Why?
Oh, don't ask me. I didn't create it. I'm not a garbage collection expert. I just try to explain the differences. And this I got from one of the guys who's working on G1, and he told me 16 gigs, this is the sweet spot. They figured that out. How they did, I don't know. This is the diagram for G1, and you see already this gets more and more complex. And still we see this STW, the stop the world pauses. So we have stop the world. Even in the ZGC, we have something like stop the world, but it's so small that we don't measure it. And we say it's a pauseless garbage collector. So this one, yeah, it's the default collector since JDK 9. So if you don't specify anything, you get this one, except it's just one CPU or only 1.8 gigabytes or less, right? Then you get the serial one. Who knows that one? Epsilon. Yeah, this is my favorite collector because it is no collector. It's the no collector collector. It is no garbage collector, but you can still use it as a garbage collector. And to make sure that you really know what you're doing, you can't just only switch it on, but you also have to enable unlock experimental VM options, right? That should tell you something, right? This is not the usual thing. Because, and in OpenJ9 we have the same. I think this is just called no collector or something. They have the same thing.
There's something called zero.
Zero GC?
Yeah.
This is ZGC, that comes. And it's not zero. It's called the Z garbage collector. Because I thought the same, but it's not. So Epsilon, you might wonder, so okay, there's no garbage collection, that's cool. Then what does it mean? That means you start your application, it allocates memory if the memory is full, out of memory exception. That's it. Try it and have fun, and you will see how often garbage collection will happen in your application. Usually it's like, start, oh, what's that? Because you can't imagine how much garbage collection we do. It's amazing. So, still, there's a good reason to have something like this. One is if you would like to measure the performance of the application code itself without the garbage collector stepping in, because this is not predictable, right? You can use this, but make sure that you exactly know how much memory you need. Otherwise, it's like gone, okay? There are companies, and I always forget the name, and I always say that in this presentation because I never look it up. It's a company in the UK, that's what I remember. They are specialized on don't produce garbage at all. This is their credo. So what they do is they reuse all the objects. This is possible. It looks terrible. Right? If you see the code, you think this is not Java. Yes, it is. It's very fast. You can use this garbage collector. Awesome. Very hard to maintain. They have even collections specialized for this kind of stuff. You might ask yourself, okay, why? Why at all? Because, like I said, high performance needs, like, as I said, high-speed trading, this is their focus. There you need the fastest possible code, right? Because it's millions of dollars that really count there, and therefore they use it. Because if you don't do garbage collection, it's the fast thing you can do. but it's also the toughest stuff you can do. If you have fun with this stuff, look it up. You will find it. I will ping it. I will check it, and then you can ping me. It's really fascinating. They blog about the code, and if you see the code, you can't believe that this is Java, because it looks absolutely ugly and terrible, but it's super fast. And they reuse all the objects, and they know how to do it, which is really hard, right? Okay, this is Epsilon. So you can...
Need an example. My friend has experience with this, not with this garbage collector, but with the application. They count all clicks with 5%, and they need a lot of performance. That's why they reuse every object.
Yeah. It's quite common when you come to high-performance applications. They do this kind of reusing objects as much as possible, because once you create it, you can keep it. You don't have to put it to the garbage collector, right? But this keeping the object and reuse it is not so easy like it sounds. Right? So it's a little bit tricky, but you can do it.
It's not Java style.
No, it's not Java style. It's like malloc without free. Right? You just do malloc and then see how far you can get with this. Okay, leads me to Shenandoah. Did someone heard about that one? It's from Red Hat. Roman Kenko was one of the developers there. He's now at AWS. This is the only collector for the next, what is it, 5 days? When do we have JDK 24? Next Tuesday.
5 days.
At the moment, this is the only collector in the JDK that is non-generational. But this will change next Tuesday. So there will be the first version of a generational Shenandoah. That means it will be even faster than it is now. I think at the moment they guarantee 15 milliseconds as the max pause, but usually they are way below that, like 5 milliseconds, sometimes 1 millisecond. But it's made for very large heaps. It's fully concurrent. They use a new barrier concept there. They also use the Brooks pointer for the concurrent copying stuff. It's made for latency sensitive applications or large scale systems. It's more or less pretty much the same approach that ZGC uses, right? Or not the approach, it's the same idea, but they use a different approach of doing that. But they have the same goals. And large heap means 100 gigabyte plus. You see that the CPU overhead is even bigger now, so 10 to 20%. So what does it mean? So probably you heard about a company named Netflix, right? And because we have microservices, thanks. Right, just for them. It doesn't make sense for everyone, but everyone uses it because they do. And they did a blog post about, oh, we switched everything to ZGC. It's cool. It's great. We just see a performance drop of 3%. Okay. If you let that sink in and you think about the machines that they use, it's not your typical server, right? It's huge. They are the biggest customer in AWS. And it's a customer of Azure, so that's why I know. You can't really compare that with your company, except you are huge and you have this demand for scaling and all these kind of things. So when they say they switched to ZGC and just saw a drop of 3% in performance, yeah, that's cool, but they have the machines to do that, because these garbage collectors, starting with Shenandoah and also ZGC, they really shine if they have lots of CPUs. And lots, I mean 80 cores, maybe more if you have. Right? If you have 512 gigs of RAM, cool. More is even better, right? Then these garbage collectors are really good. If you put them on a machine like this, or even smaller, let's say a Raspberry Pi, you might laugh, Raspberry Pi. But this is more or less your microservice, right? You have 2 cores, maybe 4. You have 4 gigs of RAM, maybe 2. This is more or less a Raspberry Pi. So if you use it on these devices, you will see, oh, something strange happens. Let's say you have 2 cores. This is a fully concurrent collector. What will happen? Bam, you only have 1 core left, because the other core is used for garbage collection. Whoops, 50% performance lost. So not 3%, it's 50% in this case. This is the stuff you have to think about, right? When they say it's 3%, that means they have machines like 256 cores. Yeah, okay. We see 3% drop in performance. Even 3%. If you have to pay for 3%, because if you would like to keep up with the performance, means a lot of money you have to spend, right? For Netflix, it's okay. For your company, not not in any case, right? So you have to keep these things in mind. Be careful if such companies say, oh, it's cool, just switch to ZGC. It really depends on where you use it. I was in Seattle the day before yesterday and talked to someone, and they said it's a big company in the travel area, so a huge company. And they have problems with ZGC because they struggle. They see performance drops and other stuff because they don't have the appropriate machines to run it on. Right? So it's really, you have to be careful with this. And nobody tells you, right? Oracle just said, oh, this is the best garbage collector ever. Yeah, it's a new one, it's good. And there's something specific to that one that I will come to. But it's not for everyone. Right? You can try, but don't expect it to be the one weapon, the silver bullet. It's not in all cases. Doesn't mean it's a good collector. This is a great collector for a specific use case. You see, it's made for large heaps, right? And we saw nobody use a 64, so it doesn't really make sense for you, maybe. Leads me to this one, the Z garbage collector, right, which is the newest one. And I won't go into detail because this is a copy of another collector. And yeah, shameless plug, it's a copy of our collector that Zul invented that, I think, 14 years ago. And there's a paper on the web, you can read it, probably Oracle did it, because if you see the implementation and you read the paper, you say, oh, this is the same, right? So it's the same implementation. We have only 2 generations. We don't have survivor spaces here. We have young and old generation. And with next week's JDK, the non-generational version of ZGC will be removed. It's not available anymore. At the moment, you can still switch it on, but in JDK 24, it's not available anymore because it's slower. It doesn't make sense. So this one is, again, very much the same as Shenandoah from the resources and all that. It's made for terabytes of heap. So I think they guarantee around 1 millisecond garbage collection pauses, so it's really fast. But it needs CPU and it needs memory. Right? This is, if you really would like to see the performance, you need a big machine. But if you are aiming for low latency applications or something like large scale, highly concurrent, then this is a good collector, definitely. But in this case, usually you have also the machines to do that. That should be it with this one, because C4, the one that we created, is exactly, the ZGC is a copy of that, except one thing. And that everything that I tell you now also applies to ZGC, except that it's not part of Zing, which is our own JVM. So what we use, it's a so-called loaded value barrier, which is this read-write barrier thing. And Oracle names it colored pointers. So if you look up ZGC, you see always like colored pointers. This is what we call loaded value barrier, same thing. It's a read-write barrier, yeah, and if you use it on Linux, you should enable transparent huge pages because then you get bigger memory pages. This also applies to ZGC. So, and now let me tell you about the things that makes this collector special. So, like I said, this also applies to ZGC, same thing. So we have multiple garbage collector threads, right? It's not one, it's multiple. They work concurrently. And keep in mind, and I mentioned that already, as soon as you use a fully concurrent garbage collector, you need some parts of your CPUs to do the garbage collection at the same time. That means you don't have the full performance, right? Compared to parallel GC, where you have all the threads for your application, and then you have a short pause, and then again you have all the threads. Here you always have, let's say you have 100 threads, 20 you need for garbage collection, right? Okay, so we have garbage collection threads. They start following the references from the stack frames into the heap. They find all this, they trigger the LVB, no problem. And then suddenly the applications thread steps in and say, I would like to allocate memory. So now the difference to all the other collectors here is the application thread will allocate this empty memory cell and it will trigger this loaded value barrier colored pointer, right? And that leads to the fact it triggers the LVB and then it will mark, and this is the instruction that we do. It's test and jump. Test means it checks, is it a reference? If yes, follow. Can I reach it? If yes, mark it. If no, do something else. But this is not important. This is just one CPU instruction. So it will trigger the LVB and then it will be marked automatically. So without the garbage collector, it doesn't have to do it. It will be marked by the LVB. That's the difference here. So that looks like the application thread and the garbage collector work hand in hand. because also the application thread can mark stuff as live. As soon as it allocates, it can mark it. And this is done by the colored pointer or LVB. So then it passes over the information to the garbage collector, and then it knows, okay, there's a new live memory cell, right? So that means there is no remarking phase needed in this case. That's the big advantage here, if we do concurrent marking. That's the one difference. The other one is called quick release, and that's, I mentioned when we do the concurrent copying, that we can't remove the original memory object as long as we don't update all the references, right? That means we have to keep both objects in the memory. There's a different approach here. You see we have virtual memory and we have physical memory, which is the purple one. And now we start moving objects around. And in the old approach that I showed you before, the forwarding header is in the old object. There's the information, where's the new object? And so you have to trigger the old one to find the new one, okay? Here it's now different. So what we do is, and ZGC the same, we copy the forwarding information in an off-heap page. So it's not in the old object, it's somewhere else, and it's always the same area in the memory. And then we copy stuff. As soon as we copied everything out of one area, we can directly reuse the physical memory that's below that. That means we don't have the problem that we run out of memory, because this is concurrent, right? At the same time, the allocation is going on, so every physical memory that's available is important. To be fast, you have to free memory as fast as possible. So we can release physical memory directly after everything was copied out of it, because then it's directly available again. So what will happen is, if now an application thread steps in, following the old reference to the old position, it does trigger the LVB, test and jump. It tries to test if this reference is still valid. It finds no, it's not. And then it looks it up here, right? And then it updates the reference in the object automatically. So every next thread that tries to access the old one won't find it anymore, because then it's already updated to the new one. This is the so-called self-healing process. In addition, everything that is in this off-heap page will be handled by separate threads. They will also update the references concurrently. So this is just only needed if there's a reference that was not updated yet, and then the application that tries to access it and doesn't find it, the LVB or the colored pointer will put it to this one, to this position, read it from there and update it. That's the idea. Okay. Like I said, the customer with the biggest heap that we have has 21 terabyte of heap, and we still have garbage collection pauses below 1 millisecond in this heap.
So is that memory on one machine, or
It's one machine. Yeah, it's huge. This is someone that is on the stock exchange. So they use these kind of machines, which is really crazy. You see the overhead, it's the same as with the ZGC. I won't go into detail. We only support it on Linux, and the reason is that we found out that the memory access in Linux can be faster. So our CTO, which is a really smart guy, he figured out that if we tweak the memory access in the operating system, we can do 1 million times faster memory access, and we have a benchmark that proves it. And this is only possible on Linux. This is the reason why we do that only on Linux and not on Windows and Mac. So, and this is the diagram. We don't talk about it. Forget about it. One thing that I have to mention here is that I told you that if you do concurrent garbage collection, you see a drop in performance. And our CTO who created the algorithm figured that out, and then he said, okay, we have to keep up with this. So we created a new compiler that does more aggressive optimizations to the code, so the code is faster, so we can keep up again. So we can be even faster than before with this compiler. And that's the difference in the Zing JVM. So we have a different compiler and the different garbage collector. So now this is all the garbage collectors, which is a lot, right? So the question is now, okay, which one should I choose? Most of you use G1, which works fine. We have 3 criteria. We have throughput, latency, and resource usage, and you can choose. Of course, you would choose, I take all 3, right? Sorry, you can only choose 2 out of 3. This is otherwise not possible. You can say, I would like to have the lowest possible resource usage, and I would like to have very low latency. Sorry, throughput won't be high, right? You can say, oh, I need very high throughput and very low latency. Sorry, resources would be huge. That's the problem. Doesn't really help you a lot, so this might be better. If you don't really care about pause times, well, you say, it's not critical. This service can stop for 10 seconds. Nobody will care. But I'm really concerned about the resources. Then you're on the right side of the diagram. Serial, parallel. It's a good collector here. If you really need super fast garbage collection and response times, and you don't want to have pause times, you don't care about resources, then you're on the left side of the diagram. And everything else is in the middle, and this is where you see G1, right? And this is why most of you are fine with the garbage collector that you use, right? So G1 is a good collector, but you have these extremes. It really depends on the use cases, and then it makes sense to take a look at the different collectors. Even if you are more on the right side or more on the left side, it might be worth to take a look at these other collectors and check it out. But believe me, it's not so easy. You have to really monitor your application, know exactly what it does and all these things, right? And then you can choose a collector. So I have an overview. Don't take pictures. You will get the slides anyway. And you can't read it on the pictures if you take them from the back. So this is just everything I said in more or less one diagram. You can just compare stuff and see, okay, what might be a good collector for our use case. Tooling. Because people ask me, okay, what can I use to measure this stuff? There are different tools. We have free stuff. We have stuff you have to pay for. JitWatch, does anybody know that? Very nice tool where you can attach it to a run in JVM and it will show you stuff that's going on in the JVM. Like stuff like garbage collection and things like that, which is quite good. JHiccup, this is something that our CTO wrote. This shows you hiccups, and we mean hiccups in like pauses, right? Where you can figure out, it's strange. I see some strange behavior here. So and then with this one you can measure that. Visual VM, does someone know that one? This is a quite good tool, a good start to work with this kind of stuff. Then there's GC Easy. Is someone doing garbage collection logs here? Because that's the first thing you should do. If you try to start tweaking the garbage collector, you can create garbage collection logs, and you can do that at runtime. The overhead is minimal. But with these logs, there are tools like GC Easy. We also have a tool to do that. You can then analyze the log files, and then it will tell you exactly what happens at what time and all these things. So it's lots of information, very useful in case you would like to fine-tune the garbage collector. There are also profilers like JProfiler, YourKit, Java Profiler, and stuff like that. Is anyone still interested in more? Yes? Hey, read this book. This is terrible, this book. It's so hard. It's the handbook. It's like this thick. Everything is in C. These guys cover all kinds of stuff. They not only garbage collection, they also cover reference counting, tell you the differences. They really go down into the details. So if you're interested in that, this is a good one, and you should get the last edition because the first one was from 2012, and I think it's at least 3 editions in the meantime. So they updated, and they also cover the garbage collectors that we have in the JVM. So they don't go into the very much details, but more than I did here. So it's quite interesting book, but don't expect too much out of it, except headache. Right? It's really hard to read, but okay, this is the only book you can get. There's another one from the same author, which is even more complex. I read them both, and it's hard. Why? Because it's interesting, but it's really hard to understand because it's so theoretical, and you can't simply just test it, right? And that's it. Thanks for not falling asleep. It's a tough topic.